I welcome you all to this session of thermal engineering, and the topic of our today's discussion is a brief review of the second law of thermodynamics. You know, in the last class we have briefly touched upon this aspect, and we have discussed that the objective of the second law in the context of thermodynamics essentially, and though the subject is thermal engineering and we shall be discussing about a few system, and to be I would like to say cyclic systems, I mean the systems undergoing through cyclic processes. So, but I wanted to have this discussion keeping in mind that all the processes which are there in real practice, real applications are the irreversible process. So, you know that we have studied in thermodynamics that irreversibility leads to destruction of the performance. So, our objective should be to know about this, to quantify about this, and then upon quantifying we should take some kind of measures to reduce the degree of irreversibilities associated with any particular process. You know that so what I told, we should study about this. Why? So, we know that all processes are having some degree of irreversibilities, and knowing fully that some degree of irreversibility is there or some irreversibilities are there, can't we try to study that what is the degree of irreversibility present in the process? In other way, can't we tell to what extent a real process is deviating from the reversible process? And if we really know that this particular real process is deviating from this reversible process, and this is the extent of deviation, if we can quantify, that would be good for the system. So, the next objective is coming to quantify that extent of deviation mathematically, of course, and having quantification of this particular term, we can definitely take some preventive measures, as I told you, essentially to increase the performance or efficiency of the systems. So, second law of thermodynamics is important in this context. Second law of thermodynamics provides us a mean of quantifying the degree of irreversibility present in any process. So, before going to discuss about that part, of course, not in a greater detail, but I would like to briefly touch upon that. Let us recall two important statements that we have studied in the context of second law. What are those? First is Kelvin Planck statement that you have studied. What is this statement? We have studied that it would be very difficult to have a device that will operate in a cycle and will produce no effect other than raising a weight while exchanging heat with a single thermal temperature reservoir. So, let me tell you again. Never try to memorize, rather try to understand what this statement talks about, and then try to describe it using your own sentence. So, if I try to write it, let me allow to write it. So, Kelvin Planck statement. So, Kelvin Planck statement I am writing, it is impossible to construct a device that will operate in a cycle. So, I am underlining these words, and what I told you that it is impossible to construct a device, of course, a mechanical device. In the context of this course, we can say thermal device that will operate in a cycle and will produce no effect than raising a weight while exchanging heat with single thermal reservoir. So, you know that this is the statement of second law, I mean first Kelvin Planck to be precise, and we all have studied about it. What it physically tells us? It is telling that it would be very difficult to construct a device that will operate in a cycle. I mean, if we do not include these words, then perhaps it would be possible. So, if you would like to have the cyclic process, cyclic operation, then it would be very difficult to construct a device which will produce no effect than raising a weight while exchanging heat with single temperature thermal reservoir. So, you try to understand that I should write other than raising a weight while exchanging heat with single temperature thermal reservoir. So, if we try to draw schematically one device. So, basically these two statements for second law statements of second law, two statements of second law are used in the context of either heat engine or heat pump or refrigerator. So, if it is a device which is operating in a cyclic process and while exchanging heat with single temperature thermal reservoir, say it is temperature is T H and this is T L. So, thermal reservoirs are very large. So, we can maintain the constant temperature T H, and upon receiving heat Q H, if we say W net. So, that means when it is telling something about raising a weight, so it has to do some work, and that is what you have studied in thermodynamics. So, while exchanging heat with single temperature thermal reservoir and exchanging weight will not be possible in a cyclic manner. So, that means upon receiving QH heat from this temperature reservoir, if you would like to get W net, it will not be possible. So, that means some amount of heat must be rejected by this device to another reservoir. So, this QL will be there. You know that we have studied about this efficiency, thermal efficiency. So, 1 minus QL divided by QH, right. So, you see that here if we assume all the processes are reversible process, we can write W net equal to QH minus QL, right. So, just we can write from first law of thermodynamics, right. So, if the processes are reversible process. So, what we can write, this is W net divided by QH. So, try to understand. So, when this second Kelvin Planck statement tells us that this QL not equal to 0, if QL equal to 0, efficiency will be 100%. You can see if QL equal to 0. So, if QL equal to 0, eta thermal equal to 100%, but Kelvin Planck statement tells us that if you would like to run this device in a cyclic manner, in a cyclic process, then efficiency cannot be 100%. So, efficiency cannot be 100% and QL should not be equal to 0. So, that means some amount of heat must be rejected to another thermal reservoir to operate this device in a cyclic process, in a cyclic manner. So, this is what this statement talks about. If we go to the another statement, that is Classier statement. It is impossible to construct a device that will operate in a cycle and produce no effect other than effective transport of heat or effective transfer of heat from low temperature thermal reservoir to high temperature thermal reservoir. So, let me write it. It is impossible to construct a device that will cycle. That means the device is going to execute through a cyclic process or cyclic processes. So, and produce no effect other than transfer of heat from low temperature reservoir to high temperature thermal reservoir. Low temperature thermal reservoir to high temperature thermal reservoir. So, I am writing thermal. I would like to use one word, that is effective, effective transfer of heat. So, again this statement is again important in the, rather I would say this statement is used to cover heat pump or refrigerator. Okay. You know that if we again draw a device, and if we assume this is low temperature thermal reservoir and this is high temperature thermal reservoir, and this is drawing heat from this low temperature reservoir and supplying heat to the high temperature reservoir. So, the effective transfer of heat using this device won't be possible in a cyclic, I mean if you would like to run this device in a cyclic manner. So, essentially what we can tell you that, you know, as if you would like to transport heat from this reservoir to that reservoir, right, this is very important, and this transport of heat as if is mediated by this device, and it is not possible if the device is running in a cyclic manner. So, if you would like to have it, we must have work input to the device. So, basically by supplying work into this device, so this arrangement is such that it is now transferring heat from this low temperature thermal reservoir to high temperature thermal reservoir. Let me tell you, it is next to impossible to transfer heat from low to high temperature thermal reservoir. So, that means the spatial arrangement, let me tell you, here we are having, you know, surface boundary, you know, that is, you know, surface, and at these two surfaces here temperature is QL minus delta L, and here temperature is QH plus delta H. So, the temperature at this surface must be greater than, sorry, it should be temperature, temperature delta H, and this is T. So, the temperature at the surface must be higher than TH, and temperature at the surface must be lower than temperature TL, and it is because of this arrangement it would be possible to transfer heat continuously from this low temperature reservoir to the high temperature reservoir. So, if you would like to have it, we need to have this special arrangement, and as if, you know, this arrangement, you know, is, so basically the transport of heat, that is from lower reservoir to higher reservoir, is mediated by this arrangement, and to run this device we need to supply continuously energy by work, and W in will be there. So, you know, so this covers, as I told you, heat pump and refrigerator, and I am telling, you know, that for this particular case, you know, that it is, we need to define something called coefficient of performance. So, COP. So, if it is, I mean this device can be used to represent the, you know, refrigerator or also heat pump. So, the COP of refrigerator will be QL divided by W in. So, essentially at the cost of this input energy by work, how much energy in terms of heat we can transport, so that this space can be refrigerated, and that is why this COP is defined. Now, question is why it is COP, because QL, our objective should be to reduce more amount of QL to refrigerated space. So, basically COP of refrigerator is, I mean, greater than 1, because QL is higher than W in, and you know that, so basically unity. So, basically if you would like to define it as efficiency, it is, you know, kind of it looks odd to have efficiency higher than 1. So, we have studied about efficiency in the you know, in the context of hydraulic machines in different paradigms. So, basically efficiency we know that it should be, it cannot be more than 100%, that is what we have seen in the last slide. So, if we define it as the efficiency, it looks odd. So, to avoid that, the coefficient of performance is coming into the picture. So, basically you know that this is basically this quantity is greater than 1, and to make it different from the efficiency, this coefficient of performance is coming into the picture. Okay. So, this is what is important, and you know that this coefficient of performance for the heat pump will be Q H divided by W in. So, basically I would like to supply heat to this space. So, you know I need to pump heat. So, that is why heat pump is coming, and if you would like to pump heat, so this device will run and we need to supply energy to the device. Why I am discussing about these two statements again, because these are very trivial. You have studied about all these in the context of basic thermodynamics course, but if you go back to my previous slide, you know that if we go to the previous slide, what I have written over here is that this is used to, so this is used to, this covers heat engines. Now, why I am telling it, because very soon we shall start discussing about steam power cycle, and if you would like to get continuous supply of electricity from the power plant. So, that means it is a continuous process. So, maybe just for example, I am giving you, because you know that to get electricity what we need to do, either in a thermal power plant or if it is a hydel power plant, we need to have continuous supply of energy. So, basically in a thermal power plant what is done, by burning coal, that energy is given to a place wherein water is getting converted into, or rather water gets converted into steam, and that steam is taken to another device wherein it does work on the rotating part of the machine and we are getting electricity. So, if you would like to have continuous supply or continuous work output from this particular cycle, there must be a place wherein some amount of energy should be rejected. So, keep in mind, again I will be discussing this part relating this particular statement when we shall be discussing about steam power cycle. Okay. So, now question is very important term I am going to discuss now, very important aspect rather I am going to discuss now. You know that we have talked about this Kelvin Planck statement and also the Classier statement. Again I am coming back to that particular point, that if we really would like to know the extent of deviation of all the processes from the reversible one. So, you know that when I have written this, or here we have assumed that all the processes are reversible. So, in reality it is very difficult to achieve a reversible process. So, all processes are irreversible. Now, keeping that in mind, our objective should be to find out, to define or to quantify the degree of irreversibility present in a process, and that is done using this second law. You know that very important, we have seen that one important, what I am telling you, that in the context of thermodynamics you have studied that one most classical inequality that you have studied in thermodynamics, that is the Clausius inequality. So, I am trying to discuss about the Clausius inequality. So, what is this? So, this is one of the most classical inequalities which is studied in thermodynamics. So, this is del cube by T cyclic integral that is less than equal to 0, right. So, this is what we have studied. So, now we have discussed about heat pump or heat engine. Now, if it is all the processes are reversible, so basically this delta cube by T for the reversible processes it equal to 0. That can be established through some mathematical analysis. I am not going to do it because that is available in textbook, and this quantity delta q by T for the irreversible process is less than equal to 0, no matter whether the process is there in the context of operation of heat pump or refrigerator or heat engine. So, that is why delta q by T, if it is, if you would like to, if we calculate it for the reversible processes, the processes are getting executed following the reversible path, then it is equal to 0, while delta q by T, this quantity for irreversible processes is always less than equal to 0, no matter whether the process is getting executed in heat pump or refrigerator or heat engine. So, we can get a clue from this that perhaps this delta q by T, so this is valid for heat engines, for processes in heat engines, heat pumps and refrigerators. Okay. So, this is valid for heat engine, heat pump or refrigerator. So, what we can get to know from this, we can say that this quantity is something special. So, delta q by T is something special, and we are getting a clue that somehow if we can calculate this, it is for reversible path equal to 0 and it is for irreversible path less than 0, right. So, now say I would like to calculate this for different reversible path, right. I am not telling that whether this quantity will give us a mean of quantifying the degree of irreversibility present in the processes, but as if this quantity is giving something some indication to be precise. So, basically you know that this quantity if we try to calculate for any process which is getting executed via reversible path, it is equal to 0. If it is for the irreversible part, then less than or equal to 0. So, now let us try to find out this quantity for different reversible processes, or I mean for different reversible paths. So, if we try to calculate, say again I am trying to, so any process I would like to represent in this thermodynamics ordinate diagram, say it is x and this is y. So, x may be volume, y may be pressure, it may be entropy, it may be temperature. So, I would like to represent a particular process which is changing its state from state 1 to state 2 in this ordinate diagram. So, this is state point 1 and this is state point 2. So, what we are trying to do? We are trying to calculate this particular quantity del q by T for different reversible paths. So, say one path is like this. So, basically this is 2 and this is path A, and this is cyclic process because you know that this is cyclic integral del q by T. So, this is as I told you, this is an inequality. So, basically the system is coming back to its original position via path B. So, for reversible paths A plus B, we can write 1A to 2A, del cube by T plus 2b to 1b del cube by T equal to 0. So, it is equal to 0, cyclic integral del cube by T equal to 0. Now, a system is undergoing a cyclic process, and by virtue of this process it changes, or rather it changes state from 1 to 2, and it is again coming back to original state. So, that is a cyclic process. So, this is now what we can write? We can write for reversible path, say another. So, it is coming A plus C. We can write 1A to 2A del cube by T plus 2C to 1C del cube by T equal to 0. So, basically here path A, B and C are reversible. So, there are 3 different paths A, B and C, that these paths are reversible path. So, basically we would like to see that if you try to quantify del cube by T for different reversible process. So, the process, the system is changing its state from 1 to 2, and it is again coming back to its original state, but following different reversible path. You know that if we try to look at these two equations 1 and 2, right. So, these two equations, if we try to compare, so by comparing these two equations, what we can write? We can write 2b to 1b del cube by T equal to 2c to 1c del cube by T, right. That we can write by comparing equation 1 and 2. So, by comparing equation 1 and 2, we can write this. If we try to box it, then perhaps we are getting an important clue. So, what is this? So, try to understand, our objective was in the previous slide that find starting from, because I did not derive that this del cube by T less than equal to 0, but I am telling you, you will find it in all textbooks that this del cube by T for reversible process is equal to 0, but for irreversible process is less than equal to 0. No matter you are applying for you are calculating this quantity for reversible or irreversible processes, either occurring either in heat engine or heat pump or refrigerator. So, this is the case, and we have also discussed that probably this quantity is giving us a clue about something that probably we can measure the degree of irreversibility present in the system. So, from this very trivial exercise, we could write that this del cube by T for this path B is equal to del cube by T for this path C, and mind it, path B and path C, these two paths are reversible, right. So, what we can say that this delta cube by T, if it is for the reversible path, it is path independent, right. So, del cube by T for, if we try to calculate only for the reversible processes or the processes getting executed via reversible paths, then we can write that del cube by T reversible is path independent. So, this is very important clue, right. And now, if del cube by T is path independent, going back to this ordinate diagram, what we can tell? So, you know that del cube by T, if we try to calculate it for the reversible processes or the processes getting executed following or through the reversible paths, it does not depend on the path. So, basically it is just the difference between these 2 points, two state points. So, this is path independent, and if it is path independent, we have seen from thermodynamics that heat and work, these are path functions, these are the inexact differential, and we have written this is inexact differential, right. So, if this is path independent, that is point function, right. So, this is point function. And that is the property of the system. So, this quantity does not depend on the path, it will depend between two state points of the system. I mean the system is getting changed from state point 1 to state point 2, no matter whether the system is changing its state from 1 to 2 following path B or C, as long as paths are reversible, this del q by 2 t quantity is independent of path, and naturally then it is point function from our knowledge in thermodynamics that we have learned. If it is point function, so it is a property of the system. If it is a property of the system, I can or we can write it in the form of exact differential. So, this is d something s, and this is basically s. So, this is called the entropy of the system. So, basically you know that starting from the Clausius inequality, we could observe that that del q by t for reversible path is independent of the path, and this is nothing but this is the point function, and that is the property of the system, and we could write in this form. If it is the property of a system, we can write it in this exact differential form. So, basically we can write this del q by t via reversible path is the property of the system, that is entropy. Very interesting to note, that the right hand side of this equation, it is exact differential, while if we look at the left hand side, it is inexact differential. So, that I mean something is trying to convert this inexact differential to the exact differential. What is that? This 1 by 2 is basically just an integrating factor. So, basically that this 1 by t factor converts an inexact differential to the exact differential. Right. So, that is very important that we could arrive here that del q by t via reversible path. So, if we take several processes and if we can ensure that the processes are reversible process, then if we measure del q for the reversible process and if we try to calculate del q by t via the reversible path or over the reversible path, that is we have to integrate it, and then we will be getting this new property that is called entropy ds. So, this is very important, that this del cube by t via reversible path, it is ds. So, this is entropy. Another important thing that I would like to discuss, maybe we shall slowly come to the next part of this course. So, that this property is written in the differential form. So, entropy, I mean this equation does not talk about what entropy is physically. So, it does not talk about what is entropy itself physically, rather it gives us a clue about the change in entropy. So, let me tell you again, from this equation we are getting that there exists a property that is entropy, but this equation does not provide any mean to calculate the entropy. It does not provide the absolute sense of entropy in a quantitative manner, but it talks about the change in entropy, that is ds, differential form. So, this is very important. Now, if we consider say one process, say x y, and the state point changes from 1 to 2. So, this is the reversible process, right. If we consider this is the reversible process, right, and say another one process is shown by this is the reversible process. And this is reversible. The irreversible processes are shown by this dotted line. So, for the reversible process what we need to do? We need to calculate del cube and then we need to integrate del cube by t over the reversible path, right. So, if we try to calculate it and then we will be getting. So, basically we need to integrate it. So, because this equation does not provide the absolute sense of entropy in a quantitative manner, rather it talks about the change in entropy. So, basically what we can do, I mean if we can say process 1 to 2. So, basically if we integrate, if it is a reversible path, so this is reversible path. So, we can calculate del cube for the reversible process. If we integrate this quantity for this reversible path, then we can write S2 minus S1, that is nothing but ds, right. So, you know that this is very important. So, this S2 minus S1, that is delta cube by t via reversible path, right. I mean it changes from state point 1 to state point 2. Okay. So, this is very important. Now, from this expression what we can tell that this delta cube by t for the reversible path equal to ds. So, I have written here, that is delta cube for the reversible path or process is TdS, right. So, this is the equation that we are getting from the second law of thermodynamics. Again I am telling, I am not going to discuss in detail about several issues related to this, but just to recapitulate whatever we have learned from basic thermodynamics course, and I would like to discuss only those part which will be useful to understand the remaining content of this course. So, del cube for reversible process is TdS, right. So, this is what we are getting from the second law of thermodynamics. So, this is from second law of thermodynamics. Right. What we can write the first law, because now time has come to discuss about the combination or combine first and second law. If we try to write the equations, I mean would like to discuss about or frame equations by making use of first and second law of thermodynamics. So, first law for a control mass system we can write del cube equal to dE plus del W. So, this is first law of thermodynamics. So, this is what we can write from second law of thermodynamics, and we are writing this from first law because we have already discussed about this. Now, if we consider that changes in kinetic energy and potential energy are neglected then we can write this d equal to du. So, we can write this first law delta cube equal to du plus delta w. So, this is what we can write first law of thermodynamics for the control mass system. Right. So, now this delta Q reversible, that is TdS, and this is what we can write del Q is equal to du plus PdV. You know that if you try to write this equation for the reversible process. So, if we assume that the control mass system is undergoing a process which is reversible one. So, then this delta cube reversible equal to du plus delta W reversible, and this is very important to know that this delta W reversible is nothing but PdV. So, you have studied about that PdV. So, delta W reversible, that is the moving boundary work of a simple compressible substance in a quasi static process. So, this is PdV. So, I am writing moving boundary work delta W reversible is PdV. So, this is moving boundary work of a simple compressible substance in quasi static process. Quasi equilibrium process, right. All quasi equilibrium processes, so basically simple compressible substance, that means we are neglecting. So, if the processes, if the system is getting changed from, rather changing its state from state 1 to state 2, and it is because of this change in states, if the work done is PdV, that means if it is simple compressible substance only, then we can write this is PdV work, and moving boundary work we are excluding the other effects like electrical effect, magnetic effect. So, this is PdV work. So, we can write delta cube reversible equal to du plus PdV. You know that all reversible processes are quasi equilibrium processes. So, this is for the quasi static or quasi equilibrium processes. So, the process is occurring following rather quasi statically, almost statically. So, here this is reversible process, all reversible processes are quasi static process, but reverse is not true, that is all quasi static processes are not the reversible processes. Quasi static processes need not to be reversible processes because they might be externally irreversible. Okay. So, this is not our issue. Why I am telling, because we are writing this PdV. So, this delta W reversible we can write PdV if the process is quasi static process. So, all reversible processes are quasi static process, but all quasi static processes are not reversible process because external irreversibility might be there. So, now this is del Q reversible is equal to du plus PdV. What we have learned about this particular term? So, this term is we got from the previous slide, that is from second law, that is TdS. So, we can write TdS equal to du plus PdV. Probably this is very common equation that you have learned, and this is known as first TdS equation in the context of thermodynamics. So, this is known as first TdS equation. We also can write it entropy, internal energy in specific form, that is TdS is equal to du plus PdV. So, that is only the matter of writing whether you like to write in total form or specific form. So, this is the first TDS equation we have derived. You know that we also need to write the second TDS equation. This is very simple, because you know that this H enthalpy equal to U plus PV. So, that means dH equal to du plus PdV plus VdP. So, if we try to replace du using, if we take du equal to dH minus these quantities, so we can write TdS equal to dH minus this PdV, and minus PdV will get cancelled. So, basically minus VdP. So, this is known as second TDS equation. So, this is second TDS equation. So, basically we are using this property relationship to get the second TDS equation. So, you know that if you would like to summarize, this TDS is equal to dH plus PdV or du plus PdV or dH minus VdP. So, these two equations are obtained from the combination of first and second law, and these two equations, the first TDS equation is valid for every processes, but conceptually it is very important to note that before applying this equation for any processes, we need to integrate it over the reversible path, and then only the result of integration can be applied to any processes. So, this is the conceptual part. This equation is valid or applicable to any processes, but the conceptual thing is that we need to integrate this equation for the integrate this equation over the reversible path, and then the results of integration can be applied to any processes. So, to summarize today's class, starting from this brief description of the second law of thermodynamics, we could arrive at an equation, and that equation defining a new property, that is entropy, that is the property or point function of the system. And using that particular equation and invoking the first law of thermodynamics for the control mass system, we could establish these two important property relations, and these two important relations will be useful to several processes that we shall discuss in the several modules of this course. So, with this I stop here today, and from the next class onward we shall try to discuss about several processes from these two equations, by applying these two equations, and also by calling our conceptual understanding whatever we have learned from the first and second laws of thermodynamics. With this I stop here today. Thank you.